Guys, welcome to 20 Minutes Online Tutorials. On today's episode, we'll be discussing on first order circuit. Welcome back. In this video, we shall examine two types of simple circuits. We shall be discussing on a circuit which comprises of a resistor and a capacitor. Such a circuit we can call an RC circuit, or a circuit which consists of a resistor and an inductor. Such a circuit is what we call an RL circuit. Now, a first order circuit is characterized by a first order differential equation. There are two types of ways to excite an RC or an LL circuit. The first way is what we call a source-free circuit. Now, what it means is that the storage element in the circuit will stop flowing. How will I put it? Immediately. Like, let us say we have this. Let us say this is our circuit, our capacitor. And let's say this is our battery source. Now, when this battery source flows into this capacitor and it stops, there will be some little charges that will still be flowing out of this capacitance. Now, that charge now will flow. That same charge now will flow across the across the resistor. At the point where there's a sudden stop to the flow of current, we call that a transient circuit. Now, a source-free circuit occurs when a DC source is suddenly disconnected. The energy already stored in the capacitor is released to the resistor. Now, the voltage that flows here, we can say the voltage as a function of time, which is equal to V0, which is the initial volt, T over RC. This RC here represents the time constant. We can say time constant is equal to what? RC. So that's resistance times capacitance. Now, the key to working with a source-free RC circuit is, number one, we have to find the initial voltage V0. After finding the initial voltage V0, then we have to find the time constant. So now, let us solve an example to buttress more on this point. So now, in this figure, now let me draw a figure. So this is resistance. This is a capacitance. This is a positive and this is 0.1 farad. This is a 5 ohms farad. This is a 12 ohms farad, and this is an IX flowing down to this point, and this is an 8 ohms farad. And now they said now the VC, or the voltage across the capacitor, is equal to 15 volts. Our question is to find VC, Vx, and what? Ix. So now we first need to make the circuit conform with the standard RC circuit, the one I drew previously. So we have to get our equivalent resistance. These are the circuits should look like. 0.1 farad with the equivalent resistance. Now, these are in series, so we just add them, which is 20. And when it comes, let us say now that this now comes down to this point, and it comes in parallel with this 5 ohms resistor. It is now, we are going to now say 1 over 20 plus 1 over 5. Solving that to get our resistance equivalence, we have 20 times 5 over 20 plus 5. Solving that gives us 4 ohms. So our equivalent resistance is equal to 4 ohms. So now, after finding that, we need to get our time constant. As I said earlier, what we need to get is our V0, our initial voltage, and our time constant. Now, our time constant is equal to RC. We've gotten this is an equivalent resistance, which is equal to 4 multiplied by Coulomb. Now, our Coulomb here is what? 0.1, which gives us 0.4 seconds. So our time constant here is what? 0.4 seconds. So now we have to calculate. Let me write that down. So we'll have to now calculate our initial velocity. So our time constant is 0.4 seconds. Now our velocity, let me put it v, is equal to v naught epsilon, exponential t over. So now this is equal to 15. Remember the identity. We said that our voltage is equal to what? 15 epsilon time. Time is what we don't know over what? Over our time constant, which is 0.4. Solving this gives us 15 exponential minus 2.5 t. So after getting that, this now becomes our VC, our voltage across the capacitance. So now we now need to use the voltage divider equation to get Vx. Where is our, now this is our Vx. Vx is somewhere here. Now this one I'm going to use a voltage divider now is because this voltage X here is still in the same place with this resistance. Are you understand what I'm doing here? It's in the same place with this with the resistance, and since it is the same place with the resistance, we have to get the only voltage flowing into this section here. So getting this voltage flowing into this section, we're going to use what we call voltage dividers equation, and that's going to be Vx, which is equal to, now remember the normal convention for your Ohm's law, V is equal to what? IR, but in this case we don't have I here, so we're going to impute this our I for V over R. This R here is our equivalent, our resistance of equivalency, or how you put it. So now we have the voltage coming in. Our voltage coming in is V over our equivalence of resistance, which is, what do we get it? What do you say it is to be? 4. Yeah. No, sorry. It's going to be 20. I'm talking concerning this part. Sorry, concerning this part. These are the parts we're looking for. So we just plus the two of them because they are what? In series. So it becomes 20. Multiplied by the resistance at the point which we are looking for, the Vx, which is what? 12. Now solving that, this V here, remember the V is the same with this V here, so we then impute it. Now if you get this, it becomes 0.6 open bracket, imputing this V becomes 115 exponential minus 2.5 t. Now if you multiply this, you should have 9 exponential minus 2.5 t in volts. So we've gotten our Vx and we've gotten our Vc. Now let us get our Ix. Now our Ix, we're going to get it this way: Vx over what? R. And our Vx will be equal to what? 9 exponential 2.5 t over R. Now our arrow at this point will give us 0.7 exponential. Let me write it out. Our Ix will give us 0.7 exponential minus 2.5 t. So now in the next video we'll be studying on the source-free RL circuit. But before that, I will drop a comprehension that you can use to practice your problem solving technique in respect to RLC circuit. Bye bye.